We can say hi, Sherry.
Hi,
Sherry. Yeah, good luck at your debate tournament. Okay, so in any event, everybody, including Sherry, we've got our last type of integral. It's a line integral, although I'll tell you the truth, it's better to call it a curve integral. And the author even makes mention of that. We are going to go to parametrics, very likely, most of the time. Working with a parameter of t actually could always be done. Even though the author has a parametric in regard to x and y sometimes. But let's just say we have a curve, and it's parametric defined by x equals x of t, y equals y of t. You can see this picture here on the notes. You can see that, going from p0 to p sub n, we're going to integrate over that. By the way, this integral was invented quite a bit later. It wasn't invented by Sir Isaac Newton. It came about in the 1800s, and it was really developed to help in physics problems, honestly, in regard to fluid dynamics, fluid flow, electricity, and magnetism. So let's just say that we have a curve. Right now we'll keep it in 2D. We'll extend this to 3 dimensions on Monday and say, hey, how about we just have a parameter curve where we're even going off into 3 space, but for right now, keep it on the xy plane. And let's just say that we do have a function of x and y, and we'd like to evaluate that function over that curve. Well, my goodness, there are definite strong parallels to what we did last year. But suffice it to say, maybe we could even do this right now, talking about last year. You know what happened last year, back in the good old days? We were going through Calc AB and Calc BC, and we would integrate over an interval, wouldn't we? We would find all this area. We started with LRAM and MRAM and RRAM, and we said, hey, let's integrate over some fixed interval of x, from A to B. Well, you know what we're doing right now? We're going to integrate over a curve. We're going to integrate over a curve. And, first of all, you might immediately say, now, wait a minute. When we were integrating over that interval, it was so nice and simple. We said, hey, you could have a delta x, and, your delta x would be the width of your rectangle. And you're telling us we're going to integrate over a curve that's in the xy plane now, and I think that's the big difference. So we've got a curve on the xy plane, and all of a sudden you're saying we're going to integrate over that. Well, where's your equivalent base of a rectangle? All of a sudden you'd say that wouldn't be a delta x. No, it would be tied to arc length, wouldn't it? It would be tied to arc length. You can see this picture. We're breaking up that curve into tiny delta s's, if you would, where s is your arc length. Well, let's go back last year. Do you guys remember that for parametrics, if I wanted to find the arc length on a curve, we'd integrate from t1 to t2. Do you remember seeing this last year in BC for parametrics? Remember that? Should look oddly familiar. And yeah, that's exactly how we could find some arc length. Well, guess what? Our delta arc length is going to be this. It's this thing right here. So if we are just integrating over delta s, what you're going to see is the integral of dx dt squared plus the integral of the square root of dx dt squared plus dy dt squared, all that inside the square root, and then we got our dt. Make your substitutions of x of t and y of t in there, and then we integrate from a to b, where a and b are our t constraints. Our t constraints are right up here, aren't they? Oops, I meant to go to our highlighter. Okay? So that's tied to right over here. All right, so where are we going right now? To give you an analogy, because sometimes kids are like, well, wait a minute, you're saying that we're integrating on the xy plane. It's like our curve is on the XY plane that we had from last year, and yet our function that we have inside is a function of x and y. And immediately you'd say, that means you'd have a height of z. Yes. Guys, look at this picture. This is really a great picture to let you know what we're doing today, and actually for the next several days. Look, we're integrating over this curve, and our delta arc length is, of course, going to be, like I said before, right over here. That's a delta arc length. That's like your base of your rectangle. And by the way, that's going to be your square root of dx dt squared plus dy dt squared. But our height is going to go into 3D. So it's important to note that for a positive function f, the line integral of that function represents the area of one side of a fence or a curtain whose base is curve C and whose height above that point is f of x comma y, which of course is a z value. Okay, so you could say, here's my z value, and perhaps z is, perhaps even if you thought about it coming from a surface, well, as we're tracing that out on that curve, you can see that all of these z values up on top would be, the top of the fence, if you would. And we're just going to add up all these rectangles areas. That's what we're doing. So, with no further ado, let's take a look at an exact application. I really wanted to talk about the foundations of this, because if we gloss over it too quickly, and if we just start jumping into problems, sometimes we can lose sight as to what's really happening. Well, it says evaluate this integral sub c. Guys, for right now, that's how we're going to write our line integral. We're going to have a couple of adjustments later to have some different notation later on in the unit. But for right now, you see that, you go, I've got a line integral. I'm finding the area of one side of the fence, if you will. And you could say, well, wait a minute. I've got down below on my XY plane. Now, by the way, you don't have to make a 3D picture here. You don't. Look, here's x squared plus y squared equals 1, and I'd like to integrate this function, 2 plus x squared y ds. I'm integrating with respect to arc length, and I'd like to do the upper half of this circle. Wow. Now, we're going to parametrics. But parametrics actually have incredibly close ties to polars as well. Hint, hint, hint. So if we'd like to make a parametrization of this, guess what I might call x in terms of t? Cosine of t. Now, don't forget, so very often we're saying x equals r cosine of theta. We've worked so much with polars. You bet. Do you see that's really in a polar form as well? Do you see that? Your radius is still a 1, isn't it? And you could just say, well, I'm going to call a t in there. So I hope it's not too shocking that also, very quickly, we'd say y is equal to the sine of t. Again, that's coming directly from this as well. So wonderful parametrics right here that we're working with. And all of a sudden, kids are probably going to quickly refer back to the notes that we just had up here. And you'd say, well, wait a minute. I'm going to integrate this function from some t boundaries. Now that we have to talk about as well. We're going to say, now it's great to have our parametric equations, but we should also say, hey, I only want the top half of that circle with a radius of 1. Wow, what angles do you think we're going to go between? 0 and pi. We're going to go between 0 and pi. So, yeah, looking back up here, you could say very quickly, well, I need to integrate from a to b, so I'm going to integrate from 0 to pi. And wherever I have an x, I'm going to plug in cosine of t. So I'll say cosine of t squared. Wherever I have a y, I'll just plug in the sine of t. But remember what ds was. ds was dx dt squared plus dy dt squared. And then we'll have our square root of that. Well, real quick, what is dx dt? Help me out with that, guys. Negative sine of t. And all of a sudden, wow, with circles, this is so nice. All of a sudden, kids are going to be like, no, wait a minute. That's going to be the square root of dx dt is negative sine of t squared plus dy dt was cosine of t squared. And then all of a sudden, the light bulb goes on. You go, wait a minute. Sine squared plus cosine squared. This whole radical here is going to turn into what? A 1. Wow. That's nice. That's real nice. That happens frequently, not always. Guys, you know what? We're in last year right now. And that you even saw an AD. That's not even BC calculus. You can say, hey, let's review some AD. And my goodness, we just have to finish that out. And then we will have evaluated the line integral. Notice what I've done, though. Notice how, I do want to make a quick point here. Notice that over on the left, I started with the C. Notice that then I went back to a calculus AB integral. Do you see that? The C said, hey, you got your line integral. And then we're going to say, let's bring it back to last year's material. Let's keep it nice and simple. So, how did we do this problem last year? What do you think? We're going to substitution, absolutely. What do you think we should let u equal? Yeah, let's let u equal cosine of t. That means du is equal to negative sine of t dt. And real quickly, you could say, oh, wow, look at all that. Real quickly, and of course, we can be very, very careful. Sometimes kids will say, I just want to separate this into a different integral. And we'll change the bounds here. This becomes u squared. And then we'll say, bring out the negative. And let's see, change our boundaries. What's the cosine of pi? That's negative 1. What was the cosine of 0? A 1. Wow, look at that. Plug in a 0. Cosine of 0 was 1. Cosine of pi was negative 1. Hey, look at that. By the way, if you'd like to, you could just change that negative back into a positive and say, let's just keep it nice and simple. Oh, and forgive me, that's no longer a dt, is it? That's going to be a du. Okay? Right here, you could say this is 2t. We're going to evaluate that between pi and 0. You could say, hey, that's 2 pi. This right here, if we're really on our toes, you can also say this is an even function. So if, dare I say, why don't we just double going from 0 to 1 of u squared du. That would keep it nice and simple. And this becomes u cubed over 3 evaluated between 1 and 0. So this becomes 2 times 1/3. It just becomes 2/3. And that's what we get for our final answer. So yeah, you got a 2 pi in there. That's coming from the 2. But then you also have your 2/3 as the last part. We doing okay? All right, so that's how you do a line integral. You got to get a parametric equation for x and for y. You got to get boundaries for your t. You throw in your arc length adaptation, if you would, and make that all work out, and then you're good to go. All right, so tell you what, I'm going to stop the video.